Now most of the problems which we are interested to prove that they are hard, which means there is no polynomial time algorithm is for most of the problems, right? These are all optimization problems, which means maybe there is a problem. I'm just taking some examples. There could be many such problems. I'm just giving you few examples. These are the type of problems which we are interested in proving that they are difficult to solve or they are hard to solve, which means I want to prove that there might not be any polynomial time algorithms for this. So some of the problems are like this. Given a graph, given some graph, now what we are interested is weighted graph. We want to find out what is the shortest path which is covering all the vertices exactly once and coming back, which is nothing but traveling salesman problem, right? So I would like to find out the shortest path in traveling salesman problem, which means given a graph G, what is the shortest path, length of the shortest path covering all vertices exactly once. This is the traveling salesman problem, and we found out that the best known algorithm, the dynamic programming. So see, one more thing, whenever the problem is hard, if there is algorithm and if it is hard, we generally go for dynamic programming, and sometimes dynamic programming might not be able to solve it in polynomial time, right? But then it will give you some algorithm which is not polynomial, but still you will be able to run the algorithm, right? And traveling salesman problem is one such. And other one is maybe you can have 0-1 knapsack, right? So 0-1 knapsack is given the capacity, profits and weights, find out the combination, find out the maximum profit we could get, right? Maximum profit we could get from this, right? So again, for this problem also we have seen that we are having dynamic programming algorithm, and it is going to take a very long time, right? So which is not polynomial. And now we have one more problem called as longest common subsequence. Why am I taking these problems is because we have seen all these problems and we have seen that there is no polynomial time algorithm for this, right? That is why I am taking all these problems. Now for longest common subsequence problem also, given two sequences A and B, right? The question is find the longest common subsequence. For example, if it is A, B, B and the other one is A, B, C, D, what is the longest common subsequence between these two? It is AB, right? Because choose AB here and choose AB here, that is the longest common subsequence, right? And here, given a graph, what is the shortest path? For example, if the graph is like this, if the graph is 1, 1, 1, 1, 2, 2. Now, if you start from here, what is the shortest path which covers all the vertices and come back to the same one? So you will say that the shortest path for this problem is A to B, B to C, C to D and D to A. This is the shortest path that the traveling salesman should follow, right? And for example, for this one, if you are given two profits and weights, what is the maximum is, let us say the capacity is 10, right? And maybe you have three items given, and the profit of each item is like that. 10 is the profit, 5 is the weight, and maybe 5 is the profit, 2 is the weight, and 5 is the profit, 6 is the weight, right? Then what is the solution for this? The solution is 15 is the profit you could get if you are going to go with these two items, right? So what are the two items? This 10 and this, or maybe if it is even 6 is the weight and 6, right? Then 15 is the profit if you go with these two items, 5 plus 2, and then you cannot put this one, right? So anyway, in all the items, so what is the answer here? You put the item 1 and then item 2. So anyway, what you could see is these are all some kind of optimization problems. Here I am trying to find out the shortest path, here I am trying to find out the maximum profit, and here I am going to find out the longest common subsequence. Optimization means either we are trying to increase some value or we are trying to decrease some value, and for such problems we are interested to know whether it is easy or hard, whether it is tractable or intractable, right? So what we do is, generally talking about these problems directly is somewhat difficult. So we try to see one thing, when if you have to say that a problem is hard, then it is very easy to take a problem which is easier than this and then prove that that easier problem is hard, therefore this problem is hard. Okay, my words might be confusing. I'll just take the example and explain you. See this? Now all these problems are called as, this class of problems are called as optimization problems. Optimization problem is, given a problem we want to find out the optimal solution, and for every optimization problem we could find out a smaller problem, which means simpler problem. We could simplify a optimization problem into some other problem, and then we shall work on those problems and then prove that these problems are difficult, right? Okay, I'll take the example and show you. See, for the traveling salesman problem, I'll try to find out, I'll try to find out whether it is easy or not in some other way. The same problem, what I'll do is, I'll ask the same problem in some other way like this. Is there any shortest path covering all vertices of length k? Which means, instead of solving this problem, I am asking you the problem of, is there some of length, let us say at most k, at most k. So what is that I am asking is, instead of solving the original problem, I am framing a different problem. In this problem what I am interested is, don't tell me the answer, I don't want the answer, just tell me yes or no. Will you be able to find it out or no? So this question is there any shortest path covering all the vertices which is of length? Okay, you understand this? What I mean to ask is, in this graph, can you ever find out a shortest path whose length is some value k, and that length should be able to cover, that path should be able to cover all the vertices exactly once. So now the answer to this problem is either yes or no, right? So for example, I can ask you, is there any path in this shortest path whose length is at most 5, that you could cover all the vertices exactly once? In order to answer that problem, you find out the shortest path and then you find out the weight. Here you found out the weight is 4, and what is the question I am asking you? Can you find out a path whose weight is 5? Therefore, if you can answer this problem, you will be able to answer this problem. Or the relativeness, just compare the hardness. Which one do you think is harder? This one is harder. The reason is, once you solve this one is easier to solve. Or if you are not able to solve this problem, don't think about solving this problem at all. If you are not able to say that whether there exists a path which is of length 5, you cannot find out the path which is of length 5. If you are not able to say yes or no, you cannot find the solution, isn't it? Therefore, in some sense, this problem is easier compared to this problem. The reason is, if you cannot solve this problem in polynomial time, don't think about solving this problem in polynomial time. Why? If you are not able to say yes or no, yes there is a path, or no there is no path, then how can you trace out the path and find out the path, right? So it is bit confusing to you. You might think that, since we are solving this problem in order to answer this problem, you might feel that this problem is difficult, but no, this problem is easy. The reason is, if you cannot solve this problem, you cannot solve that problem. That is the reason. Okay, I don't know whether you are following it or not. It is very simple. See this: if you cannot answer a question with yes or no, then you cannot answer a question with a solution like this. So just to tell you in simple words, let us say I'll ask you this question first. Are you very perfect in algorithms? Let us say you said yes. Then I'll ask you some question and then you'll say the answer. But if you say no, or if you are not able to answer that question, then you cannot answer all the questions, right? I don't know whether my example is good or wrong, but then I'm just trying to make it simple. Let's see, with more examples it must be simple. See, if this is the optimization problem, then these problems are called as decision problems. Decision problem means the problems which will have yes or no answer. Therefore, what I mean to say is, for every optimization problem, you can convert it into a decision problem, and you could work on this decision problem before you work on the optimization problem. If the decision problem itself turned out to be hard, then definitely the optimization problem is also hard. The reason is, if you cannot solve this one, don't think about solving this one, right? That is the point I wanted to make. And now here for 0-1 knapsack also you could do the same thing, right? So given the problem, you can say that, is there any solution whose profit is at least, I can frame it as at least k, right? So which means, instead of asking you to find out the maximum profit, what I could ask is, do you have any solution whose profit is at least 11? Now if you can answer that question first, and if you can say that yes, there is a solution whose value is 11, then only you can answer this solution, this problem, right? So unless you answer the decision problem easily, you cannot solve this one easily, right? Which means, I told you in a wrong way. See, if this is hard, then definitely this problem is hard, or if this is easy, then this problem is easy. Okay, first let me finish this, and then I'll write the terminology what I am talking about. Now, longest common subsequence problem, think about it. So the other way of asking this is there any subsequence whose length is at least k. So observe these words, at least, at most. When I am trying to minimize some value, then I am going to use at most, which means with a upper bound. I'll give you some upper bound. Now I'll ask you to show me whether this upper bound is possible or not. When the problem is about maximizing, then I'll give you a lower bound, and then I'll ask you, can you raise the solution which is above this? Can you find out any solution which is above this, right? Therefore, what my point is here, for every optimization problem, there is a decision problem, which means you could convert a optimization problem into a simpler problem. And now if that simpler problem itself is hard, then definitely the main problem is hard. That is what I wanted to say. Why are we doing this is, it is very easy for us to form the theory based on the decision problems rather than on optimization problems. The reason is, decision problems will have simple answer, yes or no, but optimization problems have a big answer, right? Therefore it is very difficult to analyze or compare two questions, right? But if you have all the decision problems, then it is very easy to compare two questions and talk about their relative hardness, right? So the entire point of this, see, one thing is, the algorithms, the design and analysis of algorithms is all about finding the simple solutions to a problem. But then coming to NP completeness, here we are not trying to find out a simple solution, or here we are not trying to prove that a problem is solvable. Here I want to find out that show that a problem is difficult, right? So for that reason, every optimization question can be converted into a decision problem like this. What is the main difference? Optimization problem will have a solution like this, and decision problem will have yes or no like this, right? So what we shall see is, what is the relationship between the actual optimization problem and the decision problem. We shall see that now, and later we shall form the concrete basis for the completeness, NP completeness theory. Okay.